Hi, I'm Adrian. I'll be talking about hierarchical, navigable, small world, and vector databases. This is drawn from the literature, efficient and robust approximate nearest neighbor search using hierarchical, navigable, small world graphs by Malkov and Yashino. And before I get too into the weeds of this, I kind of want to motivate why this is such a cool innovation. So we could imagine that we're a large tech company that has access to a bunch of textual documents, and we perhaps want to sort them based on some thematic property. Let's say we have some theme and we want to return all the other textual documents that share that theme, but there's no way to semantically search through an S3 blob storage. So one way that we could get around this is that when we do data ingestion, we could hand label the data by theme and store those themes in a SQL store. And then when we query the database for similar thematic content, we could go through SQL and use a where clause to return the keys into S3 of all documents that share that theme. This doesn't scale very well, however, as one could imagine when we get up to about a million or more data points, these queries are very coarse-grained and would maybe return hundreds, if not thousands, of textual documents, which we would have to do post-processing to sort through. And we have no way of really ranking how semantically similar they are, besides the fact that they are the same theme. We need a more scalable approach, and that's where vector databases come in. So vector databases are essentially regular databases, but they also include vector embeddings. And vector embeddings are a cool piece of machine learning where we train an embedding model separate from the database that learns to take in some type of data input, so maybe a textual representation, and it learns to make a vector representation of the data that captures important properties of the text. So you can imagine if you have a bunch of text about tragedy, the embedding for those tragedies would be very similar and would be very contrastive to other embeddings for perhaps comedy. So those embeddings would exist on very distant parts of this vector embedding space, whereas similar things would exist very close together. And this is useful because then we can do nearest neighbor search. If we're interested in all the comedies that are related to some author, we could just search the local area of this vector embedding space and return all of the textual documents in that area. However, the process of searching these vector databases is far from trivial, and that encourages the use of these creative data structures. So how do we query and insert into vector databases? The challenges are pretty numerous. So we have embedding vectors exist in a high dimensional vector space, and navigating it is very difficult. There are potentially millions of pieces of information and data, and we need something that's very scalable, performant, and efficient most of all. So we need it to be sublinear. If we were to brute force the solution, that would look like taking the distance between every piece of data in our database with the query vector and seeing which one's the smallest, or the n smallest if we wanted n nearest neighbors. That's a linear solution. It's very infeasible if you have millions, if not billions, of data points in your database. That's where hierarchical navigable small world comes in. So it is a higher dimension version of a skip list, and I'll kind of motivate what this skip list is. So if you look at the top here, we have the skip list data structure where the bottom layer, layer 0 here, is essentially a regular linked list. We have a head node, it points to next. That has a node that points to next. That's a node that points to next. So if we traversed and we were looking for the number 7, if we started at the first head node, we would go 1, 2, 3, 4, 5, 6, 7, all the way there, which is kind of inefficient. That's a linear search. So the idea of a skip list is it kind of builds on this idea, but it has multiple layers. So it has layers 1, 2, and 3. And the idea is that as you increase your layer number, so as you go higher in this hierarchy, the representation of nodes becomes sparser. So there's a much less nodes at the top layer, but the distance between nodes becomes greater. So we can imagine that if we're searching for 7, the process for searching would be start at some random node at the top. So we're going to start at head again, just for the sake of example. We check its neighbors. It's neighbored with 1, so its next is 1. We see that 1 is actually less than 7, so we do traverse to it. So that is a successful traversal. But then we see that 1 points to nil, and nil, for the sake of example here, is just going to be infinity. And we see that infinity is in fact larger than 7, so we do not traverse to this node. Whenever we come to a local minimum like this, we then descend a layer. So now we're at layer 2. and we're still at 1. So 1 points to 4 in this case, and 4 is smaller than 7, so we do traverse to it. The same with 6. 6 is less than 7, so we traverse, but we do not traverse to nil because nil is larger than 7. So again, we hit a minimum and we drop down a layer. We see that the next is 9, which is larger than 7, so we do not traverse to it, and instead drop down again. And now the next is 7, so we traverse to it, and we have successfully found 7. Although that may have seemed like a lot of steps, this is actually a lot more efficient when you have millions and millions of pieces of data. Because imagine a jump in the case of millions of pieces of data here. Instead of jumping from 1 to 4, we might be jumping from 1 to 4,000. So instead of doing 1 to 2 to 3, 4,000 times, we were skipping a lot of that. And so this is kind of the idea for hierarchical navigable small world. That's the hierarchical part, where each of the layers is a hierarchy. The navigable small world is a n-dimensional representation of this kind of linked list idea. So instead of a linked list, we have a graph called a navigable small world. And the bottom layer is the most dense representation of this navigable small world, where every single data point is represented. So a singular data point here would be an embedding vector in the database, the vector database. So at the bottom layer, every single vector has a node. But as you go higher up in the layers, you have less and less of these nodes. So not every point is represented here. And so the idea here is that we're trying to query for the neighbors of this green node. And we're trying to find the nearest neighbors, but we don't want to start here at the bottom layer because it's going to take a while if we start at some random point to find this green node. So instead, we start at some random point at the very top. So we said start here at the red point, and we see that it has a neighbor, and the neighbor is way over here. And this neighbor, when we compute the distance, we use usually Euclidean distance to compute the distance between this neighbor and the green node. We see that the distance between this neighbor and the green node is actually smaller than the distance between this red node and the green node. So we traverse to this blue node over here. And once we traverse to it, we see that we've hit a local minima. So we drop down again, similar to the skip list. And then we relax the edges of this node. So it has two outgoing edges to these two nodes. And we see that this neighbor over here to the right actually has the smallest distance to the target embedding vector. So we decide to traverse to it. And once we traverse to it, we see that no other nodes it's connected to are closer to this target embedding vector. So we decide to drop because we're at a local minimum. And then we are able to traverse to this target green embedding vector. So this kind of leverages the idea of the skip list, where at the very top, the connections between nodes are very long. So you're going to be taking very wide steps, long steps through this vector space. Versus when you get to the bottom, you have very small, closer nodes, which means you take smaller steps that are a lot more precise. So it kind of leverages this long, quicker search at the top. And then as you get closer, you whittle down your searches. So it's a lot more efficient. And this actually is logarithmic in the number of nodes that you traverse. And then once you get to this target node, it's somewhat trivial. You can compare the previous nodes you visited in terms of their distance, because you've already computed them, to the nodes that are around the target node. So say we have these nodes, and we find that these are actually the three closest nodes. So we just return that from our query. And those are the three nearest neighbors in this vector space. And these are approximately the nearest neighbors. They're not guaranteed to be the closest. That's why it's called approximate search. And yeah, that's the kind of general idea with hierarchical navigable small world. And it allows us to efficiently search for similar vectors in this vector embedding space. So moving on, implementing this on a massively parallel scale can be challenging, however. Since there was a greedy algorithm and in each step of traversing the graph, we greedily pick the closest node to the target embedding space. The process of traversing to the nearest node cannot be parallelized. However, we can parallelize using SIMD the distance computation. So once we get to a new node, we know that we have a bunch of neighbors that we need to check the distance to the target node. And each of those distance calculations can be offloaded to another thread or process. And then once we found the calculations for all the distances, the main thread can decide which one to traverse to and then repeat the process. Additionally, we can use OpenMP to parallelize searches. So if we had a million people trying to search independently, since the searches are independent, all of those can be perfectly parallel, which is great if we have like a bunch of users of our application that are all trying to search at the same time. From the literature, it seems that there are some bounds on the number of data points you can have in your database, however. It seems that hierarchical navigable small world struggles on 1 billion plus size data sets because it does take a lot of memory to compute the nearest neighbors once you get to a very low level node. So at the very bottom layer, since there are very dense representations of nodes, many nodes have many neighbors, and that takes a lot of RAM to calculate. So that becomes prohibitively computationally expensive once you have a billion plus size data sets. So that kind of leads me to my final point here, which is I've identified Spotify as kind of the ideal use case for hierarchical navigable small worlds. So brute forcing Spotify's nearly 100 million tracks for nearest neighbors is way too slow for an on-the-fly recommendation system. And they have 100 million tracks with 678 million active users. So they have more million active users than they have tracks. So clearly the upside of being able to parallelize independent searches is very good here, while also using the sublinear speed for seamless user experience on a massive scale without the bounds of RAM is ideal for Spotify, who probably has the servers and capability to stream all of this concurrently. And this is useful for almost all of their features. So when you put on a song, they're automatically going to be generating autoplay songs in the background, which is probably using some similarity search in the background, as well as playlist curation like daylist and other things, other cool features that Spotify adds. Those are constantly being added too. So they have many use cases for similarity searches, and that's kind of the ideal use of a vector database with hierarchical navigable small world. So thank you for listening to my presentation, and these are my sources.